Hello, my name is Veronique Michaud. I'm the head of the Laboratory for Processing of Advanced Composite at EPFL. And I will present today my lab and the activities that we did with the Agilis project with the Red Cross and partners at EPFL. So my laboratory is on the EPFL campus, situated in this location. And we are working on composite materials. Seen from the material science and processing side, composite materials are materials that are made of fibers typically, or some sort of reinforcement that is made with the carbon or glass fibers, for example. And they are bonded together with a glue, which is typically epoxy, it could be a polymer. And making these composites is always a challenge, of course, otherwise we would not be working on it. And we have to make them in the best possible way, that it remains really reasonably cheap, reasonably benign for the environment, and that we make sure that we process a material in a reliable fashion, and also to make sure that it fulfills all the properties that we think it should fulfill. So we work on the fundamentals of these aspects. We also work on surface interfaces and integration of functions. So we work on smart composites, but we also try to integrate other functions, like, for example, the possibility of the material to heal itself after it's been banged or bruised, that it would recover its properties. Also biocompatibility for applications such as this one, for example, which is a bone replacement, where we make a foam that mimics the bone structure, and that is stiffer, you can see on the sides, but softer and more permeable in the inside, and so on. So our work covers many application fields, ranging from mobility, typical applications for composites, planes, boats, so light weighting in all these applications. We also work on biomedical and electronic devices, and here composites are really not fiber reinforced composites, but we also look at them in the way that they are flat, multi-layer structures. Health and comfort, so biocompatible materials, as I mentioned, energy generation and storage, for example, integration of solar panels into structures, and then food science, for example, making food fibers, but also a lot of multi-layer systems for new packaging applications. And we also, like all composite materials, have activities in sports like marine and ski, since all these and tennis rackets and so on are made of composites. But we also like to present ourselves sometimes, not so much by the work that we do, but also by some of the potential applications that it has in terms of sustainability. And relevant topics from our lab are linked to the Sustainable Development Goals. For example, health and well-being. So a project we have on prosthetic foot that I will explain to you later, and low power newborn incubators. We work on responsible consumption and production. For example, we work on bio-based composites using resources from natural fibers like flax or bamboo or palm fibers, and bio-sourced resins. We work on the efficient production of composites, trying to use processes that do not require too much pressure and temperature, and on nanostructure for waste reduction. One example of these nanostructures, for example, is given here. It's synthetic material that mimics the rose petal surface, and that will just take, you see, we have pepper on the top of the surface, and then when a water droplet is put on it, it will just self-clean itself. And we also work on climate action, as I mentioned, so lightweight structures, integration of solar panels, and use of recycled material. Today, I will present to you a bit more what we do in the health and well-being work, and in particular, this work that we did with the Red Cross. So this Agilis project was a challenge from the Red Cross. They are making, since a long time, prosthetic feet with partners in Cope, which are made to, to be reasonably cheap, affordable for low-income countries, and for people who have a need of a replacement of a limb. These work well and have been quite successful, but if you want the people to be able to live a normal life, to have a possibility to walk more normally, to have a job and so on, you need a better foot that has higher mobility, better energy release. And you can find those on the market for sure in Europe and so on, but they cost around 3,000–4,000 euros. And you can go up to much higher cost if you are considering these blades that athletes that are doing Paralympic Games are wearing. They're made of composite materials, really nicely made, a lot of energy release, and then you can really jump very well. What we focused on was this intermediate tool here that most normal people would need a prosthetic foot would wear in Europe, and make it affordable. So develop a product that has all the properties, yet is in the range of less than 100 francs. Our competencies in the lab were somewhat adapted for this because we are able to work on the choice of materials, processing issues, the assembly of these materials, and then what are the mechanical properties. And we also have been working a lot in our laboratory on the technical cost analysis. So how to make sure that when we developed a new material, a new process for making a part, that the cost is actually within certain bounds, and how can we also make choices based on the cost analysis that we run in parallel of the other developments. So this was very useful for this project. Of course, we needed many other competencies. So this project was not only us, but it was a group of laboratories from EPFL who got together to answer this challenge. Among them, there was a laboratory working on design and really on the mechanics of the foot and reliability. That was the LMIF in mechanical engineering. We had another group in mechanical engineering working on biomechanics and all the aspects related to gait analysis and the prosthetic understanding. Then we had Essential Tech, which was here in the project also through the Global South knowledge, which was extremely important also in the approach that we had and the managing of this project. So what we did was get together, first of all, get some funding, which we received under the form of a grant from the Swiss Commission for Technology and Innovation. And we worked for several years together to go from this original concept, which was this first foot that actually we had worked on already many years ago with student projects together with the Red Cross to try to understand some limitations of this foot regarding they were also very weak here, and they tended after some time of use to have some cracks that were due to fatigue. So we had already worked on with them, and they had worked, of course, themselves on a lot of improvements over the years. Yet we had a complete game changer here. We still had something that looked more or less real. The cosmetic foot remained more or less the same, and durability and so on, and the compatibility, with the outside. But we had energy storage and release, which was not able in the other one, which was given by a composite blade that is just below, but we minimized the amount of long composite carbon fiber material that we put in the blade so that we could remain within the cost structure that was given to us. We also had energy storage and release. We had a C-shaped here, which is a very special shape that was optimized for better comfort and energy storage and release as well. And it's made of a material that you would never find in this type of prosthetic foot, which is more close to what you would find in automotive applications. We also have a foam inside to feel it and make it comfortable. So this foot had better mobility, better energy storage and release, and could survive also all the mechanical demanding rules that we had to fulfill. And at the end, we were able also to produce with partners some of these prototypes and test them on the field to make sure that they were actually adapted to the market. So to conclude on this project, it was a very interesting project for us. I'm very proud that I was part of this very big team that we made over this project. What was very interesting also for me as a composite material engineer in this project was that we had to go really thinking out of the box, because we could have solved this problem reasonably easily by mimicking what you find on the market. So finding a very expensive solution, which has the best mechanical properties, but is really with super high tech materials. we had to think, and with this cost structure that we had, we killed a lot of the initial ideas, and we had to be really creative to find a completely other mix of materials that in the end gave the mechanical properties that were the ones we wanted. So they were as good as other food that you find on the market, yet with a cost structure that was completely different and that was more adapted to this application. So it was a really fruitful and interesting experience to be part of this project, to do all this thought process, which we could actually apply to many other projects that we are doing, sometimes without really forcing ourselves to think about cost effectiveness in such a really rigid manner. And at the same time, we also had a lot of students involved on top of the actual team that you see here. It was a very interesting and enthusiastic type of project for most of our students who actually could use their materials knowledge, but also apply it to this type of application, which is very interesting. So with this, I would like to thank you. If you need more information, you can find the Agilis project on the websites, or you can also get in touch with us. Thank you and goodbye.